Hello, I'm Patty Simpson with Simpson Math. Let's talk about hypothesis tests. So we have some hypothesis about a population parameter. And what we do is we go out and we collect a sample from our population, and in that sample then we find a statistic. Then we're going to look to see how probable is it that we get that statistic. And that's going to help us to infer upon the whole population. So that's kind of a hypothesis test in a nutshell, but let's go through it a little bit more in detail. So first, the steps that we're going to use to perform a hypothesis test. First, we're going to state our null and alternative hypothesis. Remember that alternative hypothesis is that research hypothesis, that hypothesis we have about the population parameter. Then we're going to determine which distribution to use for the test statistic. Can we use a normal distribution? Do we need to use a student t distribution? What type of distribution are we going to use for our test statistic? What type of distribution does that test statistic belong to? Then we're going to state the level of significance. And remember, with the level of significance, it is the complement of our confidence level. 1 minus the confidence level gives us our significance level. Then, and vice versa. And then we're going to draw a conclusion and interpret our decision. We'll go into each one of those in a little more detail. Then, when can we use our normal distribution? When is it that a test statistic falls into a normal distribution? Well, first we have to collect a simple random sample when we're collecting that sample. In other words, every member of our population must have an equally likely chance of being chosen to be in that sample. Then the population standard deviation must be known in order for us to, in order for our test statistic to fall into a normal distribution. And lastly, our sample size needs to be at least 30, or the sample needs to come from a population that is already normally distributed. If those three things are true, then we can use a normal distribution because our test statistic will be part of that normal distribution. Let's look at the rejection region that we're going to use when we're performing a hypothesis test. Remember, in a hypothesis test, we have a hypothesis about a population parameter. And we go out and we collect a sample of data, and from that sample of data, we find a statistic. And we know that that statistic is part of a sampling distribution. So we're going to look at this sampling distribution, and if, when we are looking at it, if our alternative hypothesis, our research hypothesis, if we're looking for our mean to be less than, or our proportion to be less than what the null hypothesis is, then we're going to use our left-tailed test to help us to test it. So less than is over to the left, and so it only makes sense then that we're looking for a statistic that is out far enough to the left to make us think, that's not probable, or that's a little weird. So when we have our alternative hypothesis, it has our mean or our proportion less than, then we're going to have a left-tailed test. So our rejection region will be off to the left. If, however, our alternative hypothesis has the mean or proportion greater than, then we're going to be looking for a value that is off to the right, so far out there that it's statistically significant, so far out there that we go, that's weird. So then we're going to use a right-tailed test. We're going to be looking for something on the right side. And then if our alternative hypothesis shows the mean or the proportion is not equal to a value, then we don't know if it's greater than or less than either one. We're looking for just anything that's weird. Whether it's less than that or greater than that, it would be weird. So we would be looking in this area or in that area for something that's just statistically significant, so far out there that we think that's weird. And we call that a two-tailed test, where we're looking on both ends. So let's practice just drawing that rejection region for a bit. So we're going to draw the rejection region for a hypothesis test for the population mean with a given hypothesis. Assume the population standard deviation is known and the sample size is at least 30. So this assumption right here lets us know that our test statistic is going to be part of a normal sampling distribution. So when I look at it, I know that that distribution that I'm looking at is a normal distribution. So here, our null hypothesis has that the mean is equal to 5, and our alternative hypothesis is that the mean is not equal to 5. So if I were to draw that normal distribution, and I put my mean right here in the middle, that mean of 5 right there in the middle, and then I draw a normal distribution from that, then I'm going to just draw my standard deviations on there, just kind of to show that there are those deviations. 1 standard deviation below, 2 standard deviations, 3 standard deviations below. Then this, remember, is our level of significance. So we're looking for, in our hypothesis test, a level of significance that is 5%. Or we're going to have a confidence level of the complement of that, which is 95%. And that's going to tell us how far out we're looking. So here, though, we have an equal sign for our null hypothesis and a not equal sign for our alternative. So we don't know if it's going to be less than or greater than. We just don't think the mean is 5. One end or the other, we're just pretty sure it's not 5. And we want to look then for so far out there that it only happens 5% of the time. It's so improbable it only happens 5% of the time. That's what that level of significance tells us, is that probability that it will occur. And we know that when we see that 5%, so I could rewrite that as 5%, or you could think of your confidence level then as 95%. When we see that 95%, we think 2 standard deviations out because of the empirical rule. And that's how it's going to work here too. That when I see that 95% or that 5%, I'm looking for a value that's 2 standard deviations, a z-score of 2 there, 2 standard deviations out or less probable. So in other words, it could be even further out. So we're looking for a test statistic that falls that far out. Or we're looking for a test statistic below the mean so that we are performing a two-tailed test. And if we get a test statistic in either one of these regions, then if our test statistic is down here, then we're going to reject that null hypothesis. And so that's why this is called the rejection region. Or if I get a test statistic that's up here in this area, it's not very likely that that happens. And so then I say, hey, there's something weird going on, and I reject this null hypothesis. Let's look at some more examples. So here's another example. We have a null hypothesis that is less than or equal to 65. Our alternative hypothesis is greater than 65, and our level of significance is at 2.5%. Remember that that decimal is the same as 2.5%, which means that our confidence level is at 97.5%. So now if I look at that, I still am dealing with drawing the rejection region, and I still have a normal shape to my sampling distribution because my population standard deviation is known and the sample size is at least 30. Remember, when I'm drawing this rejection region, what I really need to look at is this alternative hypothesis. And in this case, I'm looking for something that is greater than 65. So that tells me I'm looking for a test statistics that is to the right, greater than, out to the right of it. So I'm going to be performing a right-tailed test. Now the question is, how far out there is statistically significant? How far out there is far enough? And the level of significance tells us that far enough value. And this 2.5%, so I'm looking for something that only happens 2.5% of the time, or the probability would be 2.5%. Well, let's think about when I'm dealing with a right-tailed test, if I had both sides, if I had the right side and the left side for that, well, if this is 2.5% and that's 2.5%, then together it would be 5%. And then I would split that in half and this would only be 2.5%. So think about that, 2.5 and 2.5 makes 5%. Well, then in the middle would be 95%. And we know from the empirical rule that when I'm dealing with 95%, I'm going out 2 standard deviations. So I'm really looking to go out 2 standard deviations. And anything to the right of that, this is 2.5% of the area under my curve. Or it only happens, we only expect it to happen 2.5% of the time, or 2.5% of my data would be to the right of that. So that level of significance tells me that I'm going out 2 standard deviations. So here my mean is 65, and I'm looking for some value that's far enough out there that it's above 2 standard deviations from the mean. And if it falls that far out there, I go, that doesn't happen very often. That's a rarity. There's something weird going on. Maybe we should reject that null hypothesis. So this is my rejection region. Let's look at another example. Here's another example. Same setup. We're looking for the rejection region. And we know that our test statistic is going to be part of a normal distribution because our standard deviation from the population is known and we have a sample size of at least 30. So then if our null hypothesis is that the mean is greater than or equal to 3.2 and our alternative hypothesis is that the mean is less than 3.2 and our level of significance is 0.0015, then we want to just draw that rejection region. Where does our test statistic that we gather from that sample, where does that fall in order for us to reject our null hypothesis? Well, we look at our alternative hypothesis and we think that it's less than that value. So that means we're going to be looking for something less than, something so far out there that we think, ooh, that's weird. So that will be to the left. So we're performing this time a left-tailed test. Now we have to decide how far out there is far enough. And the level of significance lets me know how far out there is far enough. So here that 0.0015 could be written as, remember as a percent, 0.15%. So I'm looking for something that only happens 0.15% of the time. So it's very, very rare that it occurs. So where would that be on my normal distribution? Well, I could just look on a normal calculator to look for that probability, or I know from the empirical rule a little bit about my the probability that something occurs. So if it's 0.15 on one end, if I double that, it would be 0.3 on both ends. So if I'm looking for something that would be 0.3, and remember that if that's my level of significance, then my confidence level is the complement of that. Subtract that from 1, and you get 99.7%. Well, we know when we think about this 99.7%, we think to ourselves, ooh, that's 3 standard deviations out, but based upon this empirical rule. So this level of significance tells me I'm going to go out 3 standard deviations on this side. So 1, 2, 3 standard deviations. And the probability that something occurs out there is super rare. It's only 0.15% of my area under my curve, or that probability is only 0.15% of the time. Now, if I get a test statistic that falls that far out there, I'm going to go, ooh, that's really, really rare. And that's in that rejection region, so then I would reject my null hypothesis. So if your alternative hypothesis has a less than, then we're going to do a left-tailed test like we did here. If it's a greater than, then we're going to do a right-tailed test. And if it's not equal to, then you're going to do it on both ends. Then your level of significance tells you how far out you are going. How far out is that rejection region? And I'm looking for that probability. So in this case, 0.15. In the example before that, it was 0.25 or 2.5%. And then when I was dealing with both ends, then I'm just doubling that to see. So that's how we draw that rejection region. And if our test statistic falls in there, then we say, hey, we're going to reject that null. And if it doesn't fall in there, if our test statistic's not in that rejection region, then we fail to reject the null. Let's calculate the p-value for a hypothesis test. So the p-value is just the probability that a test statistic that we have gathered occurs. How probable is it that we got that test statistic? So that's all that p-value is our probability. So for instance, if I have a null hypothesis where my mean is at greater than or equal to 60, so I'm looking at a mean here of 60, and I have an alternative hypothesis that my mean is less than 60, that means I'm going to go out, I'm going to collect my sample, and I'm going to find a statistic for that. And I'm looking for a test statistic that is less than enough, far enough out there for us to reject that null hypothesis. So we want to know, if I go out and I collect that test statistic, and once I've gathered that test statistic, my test statistic is at -2. The z-score for my test statistic is at -2. How likely is it that that occurred? Well, when I'm talking about my z-score being at a -2, I'm actually talking about the probability that it's there or further out. What is that probability from here out? So that z-score of getting a test statistic here really means I'm looking for this probability, for something as extreme as that. Well, we know from the empirical rule that 2 standard deviations out is 95% of our data is in here. So that means on the wings, it only occurs 5% of the time. But I'm only looking at half of that, and that half of that is 2.5%. So the probability that I get something as extreme as a -2 for the z-score is a 2.5%. Or our p-value, the probability that it occurs, is 2.5%. Of course, we could also write that as 0.025. These two numbers are the same number. So when we are actually performing the hypothesis test, we know that we're looking at that left-tailed test. And if we were drawing the rejection region, it would be here on the left. But is that number big enough? Is that far enough away? Is our test statistic far enough away to reject the null? Well, it kind of depends on our level of significance. Let's say that in this problem, our level of significance had been at, what if our level of significance was at 0.0015? Well, in that case, our level of significance would have been out here at -3. We would have been drawing a rejection region in this area from -3 out. Notice my test statistic is not in that rejection region. It didn't fall in that rejection region. So therefore, we would fail to reject that null. It's not far enough out there. But if my level of significance, let's say that my level of significance was something bigger than 2.5%. So let's say that that level of significance was at 0.03%. So, just a little bit more. The probability that it occurs is a little bit more. Well, if my rejection region was there, that doesn't fit nicely on the empirical rule, but it's somewhere in between this first standard deviation and the second standard deviation. So, somewhere right in here. So if my rejection region is from there out, look, my test statistic does fall in that rejection region. So in that case, I would reject the null. So my level of significance helps me to determine, I need to decide that first before I go out and collect that test statistic. And if my p-value is smaller than my level of significance, if it's smaller than my level of significance, then my test statistic was in that rejection region. And if it's bigger, then it wasn't in the rejection region and we fail to reject. So, but in this case, our p-value, since our z-score was at -2, our p-value is at 2.5%. Let's calculate another p-value. So here I have a null hypothesis of my mean is less than or equal to 1.07, and my alternative is that it's going to be greater than 1.07. So this time the mean is at 1.07, and I'm looking for a test statistic that is bigger. So in this case, I'm looking for something that's greater over here on the right. So it means I'm going to be performing a right-tailed test. And I go out, I collect my sample, I find my statistic, and we see that that test statistic has a z-score of 3. So the z-score is here at 3. So I'm looking for what's the probability that I got a test statistic that extreme, that far out there, or what's the probability from z of 3 and out? What's that area under the curve? So my p-value there, well, we know that 3 standard deviations out within 3 standard deviations is 99.7%. That means that on the wings, we only have 0.3% out here. Split that in half, and I only have 0.3 split in half. 0.3 split in half is 0.15%, or 0.0015. 0.15% and 0.0015 are the same thing. So the probability that I get something that far out is teeny tiny. It's just 0.15% of the time that that's going to happen. So then, do we reject or do we not reject? Well, that depends on our level of significance again. So this is the probability that we got that test statistic. How probable is it that our test statistic should have been that far out there? Then we decide to reject or don't reject based upon our level of significance. So again, let's say that my level of significance had been, maybe my level of significance is 2.5%. which is also 0.025. Well, in that case, if that's my level of significance, my rejection region, again, it's on the right, I'm doing a right-tailed test because of the greater than, and that rejection region would be 2.5 doubled is 5%, so on the ends it would be 5%, so I'm going out 2 standard deviations. So my rejection region would be here. Well, notice that my test statistic falls in that rejection region, so I would reject the null. Also, notice that that is larger than my p-value. So therefore, my p-value is farther out there, it's less probable. So it does fall in that rejection region. So there's the p-value for my z-score being 3 when I'm performing a right tail test. What about in this last one? Given I have the null hypothesis, the mean is 60, and my alternative hypothesis, the mean is not equal to 60. So this tells me that I'm going to be performing a two-tail test. So when I'm looking this time, I'm looking for it to be as extreme on both ends. So on these two, I only looked at one end because I was performing a left tail test and a right tail test. But here I'm going to perform a two-tail test because it's not equal to. And I want to know the p-value for my z-score being out at least a -2. So my test statistic turns up at -2, but this time, because I'm doing a two-tail test, I'm looking for the probability that it's as extreme on this end or on that end. So what's the probability that occurred, looking for as extreme on both ends? Well, that probability out 2 standard deviations, we know there's 95% of my data in here. And so subtract that and you got 5%. So my p-value this time is 5%. Notice that I'm not splitting it in half this time because I'm looking at both ends. Whereas up here, it was 99.7 to this, so there was 0.3 on either end, but then I split it in half to get that p-value. This time it's just both ends. So my p-value is 5% or 0.05. So then the question is that test statistic then far enough out there? It depends on what my level of significance is. So that level of significance combined with the p-value lets us know whether or not to reject or not. So if my level of significance was something like let's do 3%. Well, 3%, well, this is 5%, so less than that, but we know out 3 standard deviations is that 0.3%. So it's somewhere between 2 standard deviations and 3 standard deviations would be my 3%, somewhere in between there. We'd have to look at that z-score chart or a calculator to find out exactly where that would lie, what our z-score would be for that 3%. But let's just say it's about right here. Well, again, I'm looking at both ends, so either that end or this end. Notice that the z-score of a -2 does not fall in that rejection region. So that z-score of -2 would fail to reject our null. Whereas if my level of significance was, say, 7%, well, again, we know that out this far is, 68% is in here, so that would be 32% on both ends. So it's less than that, but not quite to 2 because that's 5%. So my rejection region would be something like this for 7%. Oh, now my z-score does fall in that rejection region. So the level of significance, that and the p-value help us to determine whether or not we are far enough out there. So that level of significance, we have to decide first so we know how far is too far out there. So if we know our level of significance and our p-value, then we can tell the conclusion of our hypothesis test. So if our p-value, if that probability that we got that statistic is less than our level of significance, then that means that our test statistic was far enough out there. And so it's going to be, that test statistic would be in the rejection region. So we would reject our null hypothesis. And so it would support the researcher's hypothesis. If the p-value, though, if that probability that I get that test statistic is larger than my level of significance, then it's not that probable that it happens. I would expect my test statistic to fall there. And so that means it's not unusual. It's not something weird going on. It doesn't fall in that rejection region. And so we would fail to reject the null, and it would not support our alternative hypothesis. So we can use our p-value and our level of significance to help us to determine what's the outcome of our hypothesis test. So here's an example. For a certain hypothesis test, the p-value is 0.0146. If the level of significance is 0.05, what's the conclusion of this test? So think about what that means. I don't know if this is a 2-tailed test or a 1-tailed test. I don't really know much about it. All I have is the level of significance and the p-value. But let's just pretend for a minute that it was a 2-tailed test. If it is a 2-tailed test, then I know that level of significance being 0.05 or 5%, the empirical rule tells me that that's out 2 standard deviations. So if I draw this normal curve on here, then my rejection region would be here at 2 standard deviations on both ends, if it were a 2-tailed test. We don't actually know that from that. I'm just going to give you a visualization. And this p-value then is the probability I got it, or remember, is just 1.46% of the time would that happen. So that means that my z-score or the test statistic is either way out here, it's less than the 5%. So it's either here or there, but whatever it is, it's less likely that it's going to occur. So it falls in that rejection region. My p-value here, 0.0146, is less than 0.05. That's smaller. And when my p-value is smaller than the level of significance, it tells me that it falls in the rejection region. So in this case, the conclusion of the test would be to reject the null. We would reject the null hypothesis. And we would have support then for our alternative hypothesis claim. That's rare that it would happen. Pretty rare. There's something weird going on. So we think that the null hypothesis should be rejected. In this case, we're given this null hypothesis where our mean is less than or equal to 409 and our alternative is greater than 409. And here I have a level of significance at 0.025 and my p-value is 0.0001. Well, I can actually draw, assuming this is a normal, that the test statistic is part of a normal distribution, I know a little bit from this. This greater than tells me I'm looking for something on the right end. So I'm going to be performing a right end test or a right-tailed test. And then I could go ahead and draw my rejection region because I know my level of significance is at 2.5%. So if you think about 2.5% doubled is 5%. So I know that 2.5% is out 2 standard deviations. Here's my rejection. Here, I'll do it in blue. My rejection region is there in blue. So the probability that I get something out there is only 2.5% of the time. So I'm looking at a confidence level of, I'm 90, subtract that from 1, and you've got 97.5% of the time, I'm going to get something here. Only 2.5% of the time would my test statistic fall out there. That would be unusual. It wouldn't happen that often. So if it falls in the rejection region, I'm going to reject the null. Well, my p-value is teeny tiny. It's 0.01%. So that means that my test statistic was something way out here. That rarely happens. So you want, if you're performing a hypothesis test, that would be a lot of evidence gathered that your hypothesis, that alternative hypothesis is correct. So that would be a lot of evidence towards it, to have a small p-value. The smaller the p-value, the more unusual the activity. So this p-value falls way in there. Or you could look at it and say, this p-value is smaller than my level of significance, and so therefore we're going to reject the null. So if your p-value is smaller than your level of significance, we reject the null. It means you gathered enough evidence to support that alternative hypothesis. But if your p-value is larger than your level of significance, then it means you did not, that's just something usual. We expect that to happen. So we fail to reject that null. Let's perform a hypothesis test. So here's an example. The State Education Department is considering introducing new initiatives to boost the reading levels of fourth graders. The mean reading level of fourth graders in the state over the last 5 years was a Lexile reading measure of 800 Lexile. The developers of a new program claim their techniques will raise the mean reading level more than 50 Lexile. At the end of the pilot study, a simple random sample of 900 fourth graders had a mean reading level of 856 Lexile. It's assumed that the population standard deviation is 90 Lexile. Using a 0.03 level of significance, should the study convince the Education Department of the validity of the developer's claim? We're going to perform a hypothesis to help us determine that. Remember, the first step in performing a hypothesis test is to determine the alternative and null hypothesis. So here, the program is claiming, so their alternative hypothesis, they're claiming that their reading level will increase more than 50 Lexile. Well, if they originally were at 800 Lexile and they're increasing more than 50, then they're claiming that the mean will be greater than 850 Lexile. So that's the alternative hypothesis. Then our null hypothesis is the mathematical opposite of that. So instead of greater than, we're just going to put less than with the 850. But then remember that the null hypothesis always includes the equality. Then once we've done that, we have to decide what type of distribution our test statistic will belong to. And in this case, we have collected more than 30, at least 30 in our sample size. We know the population standard deviation. It's assumed to be known. And we've performed a simple random sample so that each member of the population had an equal chance of being chosen as part of the sample. So we can use a normal distribution. We know that test statistic is going to fall into a normal distribution. That sampling distribution is going to be normal. Now that we know that, they've gone out and they've done their sample, and they've collected a sample of 900 fourth graders and tested them and found the mean. So here is our test statistic. So they collected that test statistic. So now we need to interpret the results and decide, is that test statistic enough evidence to support those researchers' claims? So what we're going to do is first let's draw our rejection region to help us to determine whether or not that's enough evidence to support the claim. So I'm going to draw my normal distribution just to give me a picture and a visual of what's happening. So remember, in our normal distribution, our mean, median, and mode are right at the beginning. I mean, our mean there is 850. Then I'm going to go out my standard deviations, 3 standard deviations there. So I'm just going to draw myself a normal curve real quick. Then I know that we are performing a right tail test. So we're looking for a test statistic that is far enough on the right to convince us that we have enough data to support that claim. So we're going to be performing a right-tailed test. So our rejection region is there going to be on the right. And how far out on the right is far enough for us to have enough evidence? Well, my level of significance is 0.03. So I'm looking for the probability that I'm out 0.03, or that's 3%. So this is 3%. It's the same as 3%. Well, I know from the empirical rule that if I go out 2 standard deviations, that out here is 5% on both ends, so that would be 2.5% just here. This is 2.5%. But I have a level of significance that's a little bit bigger than that. So it's going to be a little bit less, not all the way to 1, but it's just a little bit less than that 2.5%. Somewhere in here. If I wanted to find that exact z-score, I would go to a z-score calculator or look on my z-score chart to find out exactly that z-score for where my rejection region begins. But right now, just for our sake, we know it's somewhere in between 1 and 2, really close to that z-score of 2. So like 1.9 or something like that would be my z-score. So there's my rejection region. If my test statistic falls in that rejection region, then we're going to have enough evidence to support our claim. If it doesn't fall in that rejection region, then we would fail to reject it. We would not have enough evidence to support the claim. Okay, so now that we have that rejection region drawn based upon our level of significance, let's look and see what is our standard deviation. Remember that in the sampling distribution, our standard deviation changes. In the sampling distribution, our standard deviation of this sampling distribution is the standard deviation of our population divided by the square root of our sample size. We saw that with the central limit theorem. So I'm going to take the standard deviation of my population, which is 90, and I'm going to divide that by the square root of my sample size, which is 900. They had 900. So that 90 divided by 900, well, 90 divided by 900, the square root of 900, square root of 9 is 3, square root of 100 is 10. So 30 times 30 gives me 900. 90 divided by 30 is 3. So that tells me that my standard deviation for this sampling distribution is out 3, count by 3s. So this would be 1 standard deviation above the mean would be at 853. 2 standard deviations above the mean is 856. 3 standard deviations would be 859. Count backwards, you've got 847. Subtract 3, you've got 844. Subtract 3, and you've got 841. This is the sampling distribution that our test statistic will belong to. And we expect it, to be within these numbers 99.7% of the time. And between 844 and 856, 95% of the time, because it is that normal distribution. Now, their test statistic that they got, when they collected their sample, they got a test statistic of 856 lexile. So let's look and see where their test statistic falls. Their test statistic falls there at Z of 1, 2. So at 2 standard deviations out. Notice that their test statistic does fall in that rejection region. So we know from this that we are going to reject the null hypothesis. But let me show you a little bit more. We also know that this z-score for this particular test statistic is 2. And the probability that we get something that far out, as extreme as that, so from 2 out, is 2.5%. So the p-value of that test statistic is 2.5%. Notice that that 2.5% is smaller, 2.5% is smaller, our p-value is smaller than our level of significance at 3%. When it is smaller, that also tells us that we reject our null hypothesis. So we did gather enough evidence to show that that this researcher was correct. Now, when we interpret our results, we need to make sure that we let our reader know at what level of significance we are talking about. Because if our level of significance had been smaller, then we would not have rejected the claim. So it depends, the null hypothesis. So therefore, we need to let our reader know at what level of significance or what confidence level we're dealing with. In this case, we would tell our reader with a 3% level of significance, we reject the null and support the developer's claims. Now we implement this reading initiative throughout the entire state based upon this hypothesis test. So we've collected that test statistic and it was far enough out there. Let's do another hypothesis test. So here's an example. A recent study showed that the mean number of children for women in Europe is 1.5. A global watch group claims that German women have a mean fertility rate that is different from the mean for all of Europe. To test its claim, the group surveyed 144 German women and found that they had a mean fertility rate of 1.4 children. The population standard deviation is assumed to be 0.6. We want to know, is there sufficient evidence to support the claim made by the Global Watch Group at the 90% confidence level? Well, the first thing we do when we perform a hypothesis test is we decide on our alternative hypothesis and our null hypothesis. So in this case, we are claiming that the German women have a different fertility rate. It doesn't tell us if it's more, it doesn't tell us if it's less, it just says it's different. So mathematically, to say that, we say the mean is not equal to that 1.5 of rest of Europe. So the null hypothesis, remember, is just the mathematical opposite. So if this one's not equal to, then the mean is going to be equal to for the null hypothesis. Now, what we're going to do next is decide what distribution our test statistic will belong to. So we're looking for different clues to let us know what distribution it belongs to. And one thing we see is that we have a group that is larger than at least 30 in our sample. So we see that we've got 144 German women that have been surveyed. So that's at least 30. And we know our population standard deviation is 0.6. So this is going to be, since we know our population standard deviation, we have a sample size of at least 30, simple random sample. We know this is going to be, that sampling distribution is going to be normal. So we can use a normal distribution. So I'm going to go ahead and draw my normal distribution. Remember, with a normal distribution, our mean is right in the middle. And then we count out our standard deviations. We'll figure out what our standard deviation is here in just a second. So we're going out 1 standard deviation, 2 standard deviations. And then we have that nice symmetric bell-shaped curve. So let me draw that for us. So our distribution is going to look something like this. There's that normal distribution. And this is the distribution that our test statistic will belong to, that sampling distribution. So let's find out what is our standard deviation of that sampling distribution. Well, remember, to find out the standard deviation of a sampling distribution, the standard deviation is equal to the standard deviation of our population divided by the square root of our sample size. So here we know the standard deviation of our population is 0.6 or 6/10, and we're dividing that by the square root of our sample size. Our sample size here is 144. Well, the square root of 144 is 12, and 0.6 there are 6/10. So that's 6/10. Well, without a calculator, if I'm doing this, I'm going to multiply the top by 10 and the bottom by 10. Then I'm just going to do a little division. 6 goes into 12 2 times, 6 goes into 0 0 times, 6 goes into 6 1 time. So that's equal to 1/20th. If I wanted to write that as a decimal with tenths or hundredths, then I could make that into hundredths by multiplying this by 5. If I multiply the bottom by 5, I have to multiply the top by 5. So that's the same thing as 5/100ths. So my standard deviation is 1/20th or 5/100ths. So I'm just going to count by those 5/100ths. So if I add 5/100ths to 1 and 5/10ths, I get 1 and 55/100ths. Add another 5/100ths and I get 1.6. Add it again and I get 1.65. I'm going to subtract, so down 1 standard deviation is at 1 and 45/100ths. Subtract again and we're at 1.4. Subtract that 5/100ths again and when we're at 1.35, about 3 standard deviations. So this is the normal distribution that sample statistic is going to belong to. It's a sampling distribution. Then I know that we gathered evidence. We went out and collected that sample. We found the statistic from it. So our test statistic is going to be that 1.4. So where does 1.4 lie on here? Well, our test statistic then is here. And we're going to be looking for something as extreme as that test statistic of 1.4. And since we are looking at not equal to, we know that we are performing a two-tail test. So we're going to be looking for something as extreme as that 1.4 on both ends. So here, this looks like it's right at a z-score of a -2. And we're looking for the probability that a test statistic occurs that is that extreme on both ends. So out 2 standard deviations on the other end as well. So the p-value for my test statistic, what's the probability that occurs, that is something that is that extreme? Well, we know in here from empirical rule that 95% of my data is in here. So that means that it's 5% of the time I'm going to get something as extreme as the test statistics we got. So our p-value there is 5%. So now, is that in the rejection region or not? Are we going to reject the null or are we going to fail to reject the null? Well, that depends on our level of significance. So now I'm going to turn to my level of significance. And my level of significance, well, instead of giving us the level of significance, we have the confidence level. We know that if our confidence level is 90%, our level of significance is 100% minus that 90%, or 10%. So I'm looking for a 10% level of significance. Or you can look at that 90% level of confidence. We know that here, this is 95% level of confidence. 95% of our data is in there. So that means that 90% would be somewhere in between this 1 standard deviation and 2 standard deviations. 1 standard deviation is 68%. So somewhere in between there, closer to the 2 than the 1. So, 1.8-ish. I would have to get out and look at my z-score chart or a z-score probability calculator online in order to see for sure. But there's my rejection region on both ends because it's a two-tailed test. So now I look, did my test statistic fall within that rejection region? Yes, my p-value is smaller than my level of significance. So it is in that rejection region there was my test statistic, and so therefore we are going to reject the null. That means that we did gather enough evidence to support our claim, or the claim made by the Global Watch Group. Now, when we interpret our results for our reader or for the person that we're interpreting the results for, we need to include this 90% confidence level, or that 10% level of significance. We need to let them know how far out there was far enough for us. So I'm going to interpret the results. I'm going to say with 10% level of significance, or with 90% confidence level, significance, there is enough data and enough evidence to support the Global Watch Group's claim that German women have a different fertility rate than the rest of Europe. Here's an example. Biologists believe that the mean gestation period for Lemnis ossi is 16 weeks, with a standard deviation of 3 weeks. Dr. Clausen suspects the mean is too high based on lab observations. She collects a random sample of 36 specimens. The mean gestation in her sample is 15. Is there sufficient evidence to support Dr. Clausen's claim with a 99% confidence level? Remember, when we do a hypothesis test, the first step is to decide on our alternative hypothesis and our null hypothesis. Well, Dr. Clausen is making the claim that the mean is too high. So her hypothesis, her alternative hypothesis, is that the mean is too high. So that means that the mean is actually smaller than 16 weeks. Then our null hypothesis is just the mathematical opposite of that. If this is less than, then the mathematical opposite is greater than that 16 weeks. And remember that our null also always includes that equality. So the null hypothesis is that the mean is greater than or equal to 16. Then we have to decide on what distribution our test statistic is going to belong to. So we look for our clues to let us know what distribution it belongs to. We see that she collected a random sample of more than 30, so of at least 30 specimen or 30 samples. Then we also see that we know our population standard deviation. Our population standard deviation is 3 weeks. So since we know our population standard deviation, we collected a simple random sample, and we have at least 30 in our sample size. We know that our test statistic is going to belong to a normal distribution. That sampling distribution is going to be normal. So I'm going to draw myself a normal curve that this test statistic will belong to. Our mean goes right in the middle. That mean, median, and mode in a normal distribution are right there together. And then the normal has that nice bell-shaped curve. Something like this is what our test statistic will belong to, some distribution like that. Then we also know the standard deviation for that sampling distribution. The standard deviation for my sampling distribution is equal to the standard deviation of my population divided by the square root of my sample size. So the standard deviation of my population was 3 weeks. The sample size was 36. So 3 divided by, well, the square root of 36 is 6. So my standard deviation is 1/2 or 0.5. So I'm going to add 0.5 and subtract 0.5 to find out what my, on my normal distribution. So 16 add 0.5, that's 17, 17.5, subtract, and you got 15.5, 15, and 14.5. So there is the sampling distribution that my test statistic is going to belong to. when I look at this, I know that because we are looking at less than, we are looking at something that's smaller. We're trying to find a test statistic that is small enough, far enough out there on the left. So we're going to be performing a left-tailed test this time. And this confidence level tells me how far is far enough out there. So my confidence level is 99%. That means that my level of significance, or the probability that I'm looking for, is 1%, or 0.01 is my level of significance there. So to come out that far, well, that's pretty far out there. We're going to be going out, well, I know at two standard deviations, because that's 95% in here. On the outsides, that's 5%. Cut that in half for just a left tail, and it's 2.5. So it's further out than that. But it's not out 3 standard deviations, because 3 standard deviations, well, this is, actually it might be even further out than that, because this is 3 standard deviations is 99.7%. So out on those ends is 0.3%. No, it's not out that far, because this would be 0.1. So my rejection region is somewhere in between 2.5% and 0.15%. So, I'd have to look on my z-score chart to make sure, or on a z-score calculator to guarantee it, but my rejection region is going to be somewhere on that left-hand side there. I'm doing a left-hand test. And that 1% of my data would fall somewhere out there. Well, let's look at our test statistic and see what we gathered. So she went out, gathered her 36 specimen, looked at the data from it, and found the mean there was 15. So her test mean, her sample mean was 15, or just this sample mean that she collected. The sample mean there was 15. So her test statistic fell there. So the probability that we get something that far out there, like we said, is, because it's out 2 standard deviations, her p-value for that test statistic is going to be 2.5%. 2.5% of the time, we're going to get something there or further out, more extreme than that. So that was the probability that she got that test statistic. Well, notice that p-value is bigger than our level of significance. It does not fall in our rejection region. So since it does not fall in our rejection region, we're going to fail to reject the null. In other words, we did not collect enough evidence to show that Dr. Clausen's theory was correct, that her hypothesis was correct. So when we get ready to interpret this for our reader, we need to make sure that we include that confidence level, or that level of significance. Because if she had made her confidence level smaller, then maybe she would have rejected her null. But she had a high confidence level. So with a 99% confidence level, not enough evidence was shown, we fail to reject the null hypothesis. So Dr. Clausen's claim that it is that the mean is too high, just there wasn't enough evidence collected, at least with that 99% confidence level. So there we have performed that hypothesis test. Math Made Simple is Simpson Math. Thanks for watching.